Hi, everyone. I'm Meini from the University of Manchester. I will take this opportunity to present my recent research work with my research partners from Chongqing University. We've done both experimental and numerical investigation on the fire resistance of concrete filled steel tube columns after earthquake. The conference paper that we have submitted only presents the experimental part, but I would take this opportunity to share the numerical part and the development of design methods. The presentation comprised of 5 parts, including introduction, experimental program, final element models, design methods, and conclusions. So now let me start with a very brief introduction on the topic. Earthquake and fires are both national disasters which will bring huge losses to human society. Fire disasters often occur after a series of earthquakes in history. So the post-earthquake fire, actually it refers to the fire directly or indirectly caused by the earthquake, which is one of the most prompt and dangerous post-earthquake disasters. Once the post-earthquake fire occurs, damage to the infrastructures and the dangers to human beings could become far more significant. As a, as a type of composite structure member, concrete have been widely used in construction due to their high stiffness, high load carrying capacity, and excellent seismic performance. However, once the earthquake occurs, the infilled concrete may crack or even crash, and the post-earthquake fire would cause further decrease of load carrying capacities. Therefore, we think in order to reduce or avoid great loss caused by the post-earthquake fire, it is of significance to have a thorough understanding of the fire performance, fire resistance of the concrete filled steel tube columns after earthquake. However, there's limited studies on the fire resistance of the pre-damaged concrete filled steel tube columns. Therefore, we think that there's a need to carry out this research project. In the experimental part, we had 4 squares concrete filled steel tube columns with the same cross-section dimension, which is about 200 by 200 millimeter. The height of the specimen was 1080 millimeter. All the steel tube, they were hot rolled steel with a wall thickness of 5.7 millimeter. As shown in these figures, the steel tube were were welding to the top end of the steel plate of the steel columns, welding to a steel plate, and at the bottom of the specimen was anchored to the reinforced concrete base. And then we have 3 layers of thermocouples. They were embedded in the concrete. In terms of the material properties, they were all shown here. In terms of a test procedure, it includes 2 stages. The first stage is about a cyclic loading test at room temperature. The purpose for this test step, is to achieve different degrees of seismic damage to the specimens, which simulates the pre-damage of the structure members in the earthquake. The test devices shown here. The bottom of the specimen, they were fixed. Then the cyclic loads were supplied by the horizontal actuator, and then the compression load was applied by the vertical actuator. The cyclic loading pattern is shown in the right-hand side with different maximum loads adopting. During the test, the constant actual loads, this one, was chosen as 30% of the ultimate bearing capacity of the specimens at room temperature. And you can see that they only, in the cyclic loading test, we've only tested 3 specimens, while the T4 specimen it is a reference specimen without pre-damage. So T4 specimen will go directly to the stage 2 instead of doing the cycle loading test. And then this slide shows the pre-damages of specimens and the corresponding load displacement relationship curves. By observation, I think it's not difficult to find that as the horizontal displacement increases, the local buckling at the bottom of the columns becomes more and more serious. The second stage of test procedure is a compaction test at elevated temperature, which is to simulate the post-earthquake fire condition. So we use the transient state test that was conducting by a servo-controlled hydraulic testing machine and electron furnace. During the test, constant compression load, about 850 kilonewton, same as the one that we use at the stage 1 test, that was applied to the pre-damaged specimens. And then under the constant loads, the temperature of the furnace was increased in accordance to the ISO 834 standard fire curve. And then according to the Chinese standard of the fire resistance test methods for building elements, the test was terminating when the actual deformation of the specimen reached 1% of the total height of the specimen, or the actual deformation rate of the specimen reached 0.3% of the height of the column. Here it shows the photos of the testing specimens. It can be seen that the surface of the steel tube was deep red with some local parts of the grayish black, except the local buckling at the bottom of the specimens occurred at the cyclic loading stage. The middle part of the steel tube was found to be softened and buckled seriously in the high temperatures test, which is stage 2 test. And then after the end of test, when the steel tube was removed, we can observe the concrete core. We can see that at the bottom of the specimen, the concrete core, especially for T1 and T2 specimen, it has been crashed. But then no concrete crashes observed at the bottom of the specimens T3 and T4. And then these figures, they shows the curves of actual deformation versus the fire resistance time. The seismic damage significantly affects the fire resistance time of the specimens. That means more serious the pre-damage that will result in lower fire resistance time. That is also summarized in the table. Then final element modeling. Final element analysis package, the abacus was used throughout the study because in the experimental parts, it has stage 1 and stage 2 tests, right? So in the final element, we try to simulate this separately and then combine them after all. So we have developed a mechanical model, a temperature field model, and a coupled thermomechanical model. This is the loop, the path that we'll take. The model will first validating against experimental results by comparing horizontal displacement and force curves, and then also validating against the temperatures for each measurement points of this specimen, and also the fire resistance time. In the mechanical model, the steel tube and the concrete, they were simulating by shell element and 3D solid element, respectively. The interface between the steel tube and the concrete employs the surface-to-surface contact with the normal direction as the hard contact, and the tangential direction used in the penalty law. The bottom specimen was completely fixed. For concrete, we used the plastic damage model, the one that recommended by Professor Lin Hai Han. And then the damage factor in the concrete compressive behavior that was calculating using according to the damage theory reported in the literature. And these photos and the figures that shows the comparison of the pre-damage specimens from tests and the final element modeling. Well, these figures that shows the experimental and numerical low displacement curves. By observing the figures and photos, we can come to the conclusion that the final element model for the circuit loading performance is in good agreement with the test results. As reporting by previous researchers, the heat transfer process of the steel tube and concrete was generally not affected by external forces and deformation. Therefore, the temperature field was developed separately in this study to analyze the temperature of each node. We use the heat transfer elements for steel tube and concrete. The mesh of the concrete field model was consistent with the mechanical model. The parameters that we use in the model, they were all chosen according to the findings in the literature. And in these two figures, they shows the examples of the measured and the final element temperatures for some points. I think it's worthwhile to mention that at about 100 degrees Celsius, the concrete evaporating, that makes the temperature time curve of the concrete factor at about 100 degrees Celsius, which affects the temperature field distribution of the concrete field steel tube columns. After we validating both models, we combine them together. So we use a coupled thermomechanical model, and then we compare the actual deformation time curves obtained from the test and the coupled thermomechanical model. It is shown here. And from these curves, we can identify the resistance time, fire resistance time from the numerical model and experimental results. And it's summarized in this table, which is also the key focus of this study, the fire resistance time. And we can see that they actually very close. The model can quite accurately or closely predict the experimental results. And then the last part is about the proposed design method. The FE model was developed and validated against the test results, and a total of 84 numerical results were generating in the parametric study using the validating model. The reduction coefficients used to account for the influence of the pre-seismic damage on the fire resistance of the structure member, which is we use it as alpha. And then this coefficient, it is relating to a few aspects like the damage degree, the width to thickness ratio of the steel tube, the strength ratio of the steel to concrete, and the actual compaction ratios. By doing the regression fit, we can get the best curve, fitting curve to predict this reduction factor. And in this figure compares the seismic damage reduction coefficient calculating by the new method and the experimental numerical results. The result shows that the proposed equation is able to predict the post-earthquake fire resistance of the columns quite accurately and consistently. Last but not least is just a bit conclusion. So we In this study, we've done the experimental program. We carry out experimentals on the fire resistance of them, and we've developed finite element models. What we validating that and use it for parametric study, and then we analyze the key parameters based on the parametric study results, and finally we come up with the design methods for this new type of for the concrete filled steel tube columns under the post-earthquake fire condition. And thank you for your attention. This is the journal paper that we've published. So if you want to know more detail about the paper, you may refer to this publication. Thank you.